How you doing, guys? Welcome to another video. This is Unit 4, 4.2. What are the factors that change the rate of reaction? And this one's an important one because your practical assessment will be based on this. Let's get straight to it. So, what are the factors that change the rate of reaction? The key understandings and outcomes for this video. You need to be able to outline the reasons why manufacturers would like to speed up the rate of reaction. You need to understand the range of factors that can influence the rate of reaction. And then you need to be able to describe the action or the effect of a catalyst on a chemical process. So in the chemical industry, controlling the reaction rate is vital. Reactions that are too slow, they're not economic. Reactions that are too fast can be dangerous and are hard to control. So chemical engineers have the role of making sure that chemical reactions occur quickly, but also as cheaply as possible. A chemical reaction will only take place when reactants collide with enough energy to overcome the activation barrier, and many collisions that occur between reactant particles are unsuccessful. To increase the probability of a successful collision, we can do a number of things. We can increase the temperature, we can increase the concentration, increase the surface area, or introduce a catalyst. A couple of things that you probably do to control the reaction rate at your house is the use of an oven to speed up the cooking process, or the use of a fridge to slow down the deterioration of food. The first factor is temperature, and increasing the temperature will increase the rate of a chemical reaction. And there's two important reasons for this, not just one, two. As the temperature increases, the speed of the particles, the kinetic energy increases. As a result, there is an increased collision frequency. So the particles are moving around faster and they're colliding more often. There are more collisions. Increasing the temperature gives the particles more energy, so when they collide, there's a greater chance that they're able to break the bonds in the reactants. So it's about having more collisions, which gives you a greater chance of a successful collision, and then more chance to break the bonds in the reactants. Concentration. The term concentration refers to the amounts of reactants present in a particular solution or gas. Now I want you to think about concentration as being like cordial. When you have your cordial bottle, that is the concentrated cordial, a large amount of cordial. When you make a drink, you dilute it, so there is less cordial in the drink and more water. And it's the same for chemicals. In terms of molecules, a concentrated solution will have a larger number of molecules when compared to a dilute solution. So there's less space between the particles in a concentrated solution as compared to a dilute solution. And that has a big impact on the reaction rate. So we need to be able to describe how an increasing concentration of a solution would increase the rate of reaction. Well, the first thing, if we have a greater concentration, we simply have more particles in the same amount of solution, and that's going to lead to an increased number of collisions. So the number of collisions is going to increase. But that doesn't essentially mean that the rate is going to be faster, because we know that some collisions don't have a reaction. So we talk about probability. If we can increase the number of collisions, the probability that we increase the number of successful or fruitful collisions also increases. So we're increasing the chance of a collision producing a product. So a greater concentration means less space between the particles, there are more collisions between the particles, and a greater chance of a fruitful collision. Handwriting was a bit slow on this one. Okay, surface area. So increasing the surface area can also have an impact on the rate of reaction. Now, if we crush a large solid into a powder, that increases the surface area of the solid. A larger surface area exposes more particles at the surface, which allows for a greater number of collisions. So lumps of calcium carbonate has a smaller surface area than a calcium carbonate powder. That's because there's more particles at the surface. So when we put those reactants into a beaker, which contains an acid, for example, the acid can only react with the particles at the surface. It can't react with the ones on the inside. So that's going to slow down the process. The acid's got to pull apart all of those bits on the outside before it can get inside and react with the reactants on the inside. If we have a powder, then all of those reactants are separated and the acid can make its way into that powder and react with all of the extra particles at the surface. So if we have something with a larger surface area, we have more reactant particles at the surface, which increases the number of collisions between the two reactants, which will hopefully lead to an increase in the number of successful collisions, or there is a greater chance of successful collisions. Okay, a catalyst. Catalysts are chemicals that speed up reactions but are not consumed during the reaction. There are usually two types of catalysts. We have inorganic catalysts and organic catalysts, and they both do a similar thing. Catalysts speed up reactions in two ways. They reduce the amount of energy required to convert the reactants into products, and they make it easier for the reactant molecules to collide and form products, so they assist in the orientation. Inorganic catalysts are things like metals, ionic compounds, and specifically designed pellets and sponges and meshes that are used in the chemical industry as a surface for the reaction to take place on. An enzyme is an organic catalyst which is useful in an organic system, which is like an animal or things like that. It's in an organic environment. So these are biomolecules which have a very specific shape, and that shape allows for it to be very selective and very sensitive to a reaction. So how does a catalyst work? Well, the reactants are mixed and we have our catalyst introduced into our mixture, and then the reactants have an attraction to the surface, and we say they adsorb to the surface of the catalyst. The word adsorb means stick to. So adsorb is where I throw a pie at your face and the pie sticks to your face. That's adsorb. Absorb is where you soak something up. And I've just realized I've put those around the wrong way, so fix them up for me. So the particles adsorb to the surface of the catalyst. They make a partial bond with the surface of the catalyst. When they're in that arrangement, it makes it easier for those two reactants to now collide and have a chemical reaction. They've been put into a more familiar orientation. So the reaction occurs on the surface of the catalyst, the products are formed, and then the products move off, allowing the catalyst to regenerate itself. A couple of key points for the use of a catalyst. Catalysts do not increase the energy in a reaction. They're just a surface for the reaction to take place on. They're not consumed and can be reused, but over time the catalyst may become poisoned. An enzyme is a biological catalyst, and biological reactions would take a very long period of time if we didn't have these enzymes in our bodies. Now, biologists have used the theory of a lock and key model to discuss how an enzyme works. We can think of the enzyme as being the lock and the reactant being the key, and only a certain key will fit into a certain lock. The reactant is known as the substrate, and the enzyme is what breaks apart the substrate into the products. So once we have the right key and the right lock, those two can have an interaction where they fit perfectly into each other. You can turn the key, and that's the production of the products. So the products are formed, they then leave the catalyst, and then the catalyst is still there to go and catalyze another reaction. Enzymes, because they're biological, are very sensitive to changes in temperature, changes in pH, and the addition of other chemicals. And their selectivity is based upon their shape, that they only allow a certain substrate to come into the enzyme for a reaction. So a key outcome would be to compare inorganic and organic catalysts or enzymes. Remember that compare word gives an account of the similarities and differences between the two or more items, referring to both of them throughout. So what are the similarities between an inorganic catalyst and an enzyme? Well, they both increase the rate of reaction. That's the job of a catalyst. Another similarity is that they provide an alternate pathway for the reaction to take place on. So the reaction could take place away from the catalyst, but it provides an alternate pathway for that reaction to occur, and it's usually an easier pathway. Another similarity is that they are both reusable. Some differences. Enzymes are very selective in that they only usually catalyze one reaction. Inorganic catalysts may be used for a number of different reactions. They're not as specific as an enzyme. Another difference is that the inorganic catalysts tend to be only useful at much higher temperatures, so above room temperatures. Enzymes work at much milder temperatures, usually temperatures found inside the body, which is a lot lower than some of the inorganic catalysts that don't really start to work until about 300 or 400 degrees. So they work at much more milder temperatures. And then the final difference would be that enzymes are very sensitive, and that means that they can be altered or rendered inactive by changes in temperature, changes in pH, or the addition of other chemicals. Whereas inorganic catalysts, they tend to function at some extreme temperatures and at extreme pHs. Thanks for watching, guys. Don't forget, drop a like on the video, subscribe if you're new, and make sure you understand this sort of stuff for the practical assessment.